So I'm Emily Beverly. I'm a new faculty member at the University of Minnesota Twin Cities. So I'm going to do the first half, and then Julie is going to do the second half, talking about what we've been discussing for the paleoclimate science planning. And so our kind of goal is that these sedimentary records from, continents and coastal environments are really important for understanding the spatial and temporal scales that we have. And so this is a figure showing the last 70,000 years, but you notice the scales on the x-axis are different going back in time to kind of illustrate different time periods. So we have basically pre-industrial showing the different models that are projected depending on the different pathways that we kind of take. But the kind of main point here is that we are kind of headed for deep time periods in Earth's history kind of to hit the amount of CO2 and warming that's expected. We have to go pretty far back in time. And so the paleo data becomes really important. And these maps of the Earth on the side here are showing at different time slices in the future, kind of how the closest analog for the environment. And you can see that as we get further and further into the next couple centuries, we start to become having environments that are like the Eocene, or that there's actually no analog for. And so we're kind of pointing out some of the key time periods that we think are really important to study. The other point here is that Earth is not warming up evenly, and the hydroclimate also does not respond how we think it should. And so we need lots of studies to really understand this. Having studies that are really spread out doesn't help us as much. And there's been a lot of push in the paleoclimate community to get these records under high emission scenarios so that we can actually ground truth the models, because the models don't have data. We only have the data that we have for the historic. So testing these future climate scenarios isn't possible unless we look to the past. So this is just another version, similar version of this that same graph, but now we also have temperature on here and CO2. And the point here is that we are now at 420 parts per million. And by in the next 11 years, we're projected to hit 450, and that is going back to the time period of the Miocene climatic optimum. So, we really need to study these different climate states that have occurred in the past to really start to understand what's kind of happening. We need time periods that have, ice coverage, no ice coverage. We need a lot of different variation to really understand how this is going to affect us, not just on a global scale, but more of a regional kind of scale. And so this is becoming just increasingly relevant as our climate, we're really starting to see the effects of anthropogenic climate change. So this is a map of both marine and continental sites. And just looking at it, you can see that we have many more sites in the marine realm than the continental realm. And so the continents are still very understudied, but this is where we live. And so we need to answer some of these fundamental climate questions that remain, that really only continental scientific drilling can address. And so we really need quantitative records of climate and hydroclimate and temperature to ground truth these models. But these are very rare on timescales that are longer than a glacial or an interglacial cycle. This is not by means a complete list, so please don't yell at me if you're your site isn't on here. This is just some of the paleoclimate records that exist that have been successful, and they, we have various ranges in ages, but there's still a lot more to be done. You can see how spread out these records are. Kind of the opportunities that we see for understanding how hydroclimate is changing on a warming Earth. We need more records for time periods in Earth's past that have high CO2. We know from modeling that these regional differences make it really difficult to interpret. And from what limited data we have. And we also are suggesting that we focus on sites that, especially where integration of continental, coastal, and marine records is possible, so that we can better understand the overall system. And so some of the time periods that are important are the early Eocene, because it's very high CO2, it's pre-industrial, and it has a different tectonic configuration, as well as the Pliocene and Miocene, which also has higher CO2, but a similar tectonic configuration. So we have two questions, these are the two main questions that we came up with as a community, that are, I'm just gonna read them. What are the drivers and feedbacks of Earth's system during times when climate veered to alternative states? And the second is, what climatic teleconnections and feedbacks are revealed by past hydroclimate change on a warming Earth? Just go a little deeper into the first one. So, really the reason we need to do this is that, we are now at a point where our Earth has a lot more instrumentation and observations, and we're doing all these modelings, but it kind of gives us a false sense of security because we don't have any way to test them. And so really, we need to go back to time periods where it's evolved, the climate has evolved, and it's, sometimes as we start to study those time periods, it's very surprising how it actually responds. And so we have some suggestions on kind of time periods that would be of interest, that have very tectonic configurations, ice coverage, vegetation, and sea level, that help us understand these responses to alternative states. So Quaternary interglacials, Pliocene warm period, Miocene climatic optimum, early Eocene and the PETM, late Cretaceous warmth, and other times where the forcings and configurations are really different than today, the glacial maximum and deglaciation, as well as the Eocene-Oligocene transition. And so then the second question about these climatic is more about kind of the spatial temporal patterns, and specifically on how hydroclimate, because that's really what we have a lot of uncertainty about, is how hydroclimate is going to respond in a high CO2 Earth. So now I'm going to turn it over to Julie. She can talk about some examples.
Okay. All right, thanks for that. I just want to say, where did we come from? There's still probably some people in the room who are alive, or were, in the early years. So we had the community came together and said, let's do continental drilling for paleoclimate. And so that was in 1995. I think Emily, I calculated you were in 4th grade. Yep. Okay, so the whole idea, of course, was that one lake here and one lake there doesn't have the answer, but we actually got into this idea of transects. And so we really started 28 years ago to think about the world as a system and to try to gather records across these different climatic systems. So we come a long way, baby, I guess is the way you're supposed to put that, to where we are now. This is actually the year when Paul published a paper that showed that even millions, 100 million years ago or more, that in fact there was Milankovitch, that Milankovitch was operating at that time. So just again, think about the fact that in lifetime, we discovered that these amazing controls on Milankovitch. So of course I have to mention Lake Elgin. What did we learn from this project? What we learned when we drilled this was in fact, holy cow, here in Russia, we have evidence of super interglacials. And not just one or two, we've got 17 different super interglacials when we saw forested conditions come back around this amazing lake that's now surrounded by tundra. And since that time also, since we drilled that, if you take the climate record from Lake Elgin and you drive a climate model, guess what? The Greenland ice sheet comes and goes several times in the last 3 million years. And so now there's emerging evidence that in fact, yeah, we had a very different kind of climate history. So that is an amazing revelation, because what's happening now in 20 years, 30 years from now, we're going to lose all the sea ice in summer. What was that like in the last during previous interglacials? From what we know, at least right now, the Greenland ice sheets, is going to fall apart faster than ever. And it's that kind of paleo perspective. If it happened before, it's going to happen again. And we know that ice sheets disappear. This is Ken Miller et al.'s compilation on sea level. And many of these super interglacials coincided with very high sea level. And so knowing something about how sea level and ice sheets and continental records come together to provide that evidence of the intersection between the hemispheres, the influence on even the West Antarctic ice sheet is really important. We've also learned about, of course, the PETM. We're now have a CO2 in the atmosphere where we're almost heading out of the Pliocene toward the Miocene. And if we're not careful, we'll head into the PETM. And even though it was first discovered in the oceans, we have much higher resolution records of the PETM on land. And so how many more other areas are there like that? If you haven't thought about this, what we're doing to the planet now is 10 times faster than the PETM. Okay, so what we're doing now is worse than that event when we had mass extinctions and so on. So it was mentioned that the Earth does not act uniformly. And we can see that in modeling, but we can also see that in data. Here's some records from Africa, where just north and south of the equator, we have a history of hydroclimate that in fact, there are similarities, but there are radical differences in those. So again, I can remember being asked, well, gosh, we have Lake Baikal. Why do we need to drill Elgin, right? Well, guess what? We learned something very, very different from those two different lake systems. And even lakes that are relatively close together can give us a much better idea of the heterogeneity of the climate response and particularly hydroclimate and water. We thought we were going to fight over fossil fuels. The next thing we're going to fight over is probably water. And just to wrap up here, this is a slide to just, again, I think every single group, all the different domains that Anders talked about have similar problems of funding. These require sometimes large rig systems. Many of the targets that all of us are talking about are not on a road network. And all of us don't need this size of a drill rig either. So we need to think about that flexibility in operations, flexibility in logistics. And another important element that we haven't done enough with is public outreach. People think about NOAA and NASA. We need to do more public outreach with all of our various projects to really get people excited about what we're doing and tell them the story about all the exploration and society relevance that we have. And I'm also going to put a pitch in. We have a lot of what we're doing is on indigenous lands. And so we need to think about involving Indigenous people in what we do, and sharing that information out beyond our normal classrooms at home. So with that, thank you very much.